Alright, in this video I want to do a video, I just want to do another thing about truth tables, and I pretty much want to show how to prove either two sentences to be equivalent or something to be consistent. These two are very different. I should have, in this one I'll do this. I'm going to do these two problems for equivalence, these two problems plus, I should include a third one. But the whole thing is that equivalence, two sentences are equivalent if it's not possible that they have different truth values. If two sentences are equivalent, then it is not possible that they have different truth values. So that they're either both false or both true. And they say a set of sentences. So we're gonna do it's like a set gamma of sentences is consistent if it's possible that they all can have a truth value of t. However, I only have here problems of consistency when they're both when there's only two sentences. However, if you take a logic class, you'll probably have to do problems of like up to 3, which I'm thinking that I actually might do this one and then add a third one onto that, because I didn't even think about having a three sentenced consistency truth table. But we'll start with equivalence. So again, these can be done in full truth tables, but I'm going to do them in shortcut tables because a full truth table, we know how to do that. And I might do one or two of these as full truth tables in this video, but we'll see. So for equivalence, to prove truth functional equivalence between two or more sentences, what you have to do is you have to assign. Actually, it's 2. Or it could be 3. I think I don't recall. But for our current purposes, we assign one of them as f and one of them as t. So one of these will be t and the other one will be f. One will be assigned as t and the other will be f. And if everything works out and we have no contradictions, then these sentences are not true functionally equivalent. However, if we run into issues and contradictions, then we know that they are true functionally equivalent. So we'll do that. We'll do that first. We'll do this first problem. We have p ampersand parens q horseshoe p, and for this one we will assign a t for the whole thing, and for this one we have p wedge parens q triple bar p. We'll assign it on f here. Now, if everything works out, then these two sentences are not true functionally equivalent. One of these I've actually worked them out. One of them is true functionally equivalent, and the other is not. So, what do we know about a ampersand if the whole thing of the ampersand is t? That means that both conjuncts have to be t. So here we know that p is t. Okay, now since we know that p is t, q can be anything. But we'll go over here to find our value or truth value assignment of q. We have a disjunction or a wedge, which means or. For a disjunction to be false, both of the disjuncts have to be false. So we know that p is false, which immediately we run into issues. Which, hey, we can say, just to make the whole thing complete, we can say that q is f. But we run into issues here, because here we figured out that P is T, but here we figured out that P is F. So this one works out, but this one we totally run into issues. So therefore we know that the sentences here are truth functionally equivalent. Okay, now onto this one. So again, I'll assign an F to the ampersand and the T to the triple bar. And again, what do we know about a conjunction or a ampersand if it's... No, I want to do it the other way around. We want to assign the ampersand a T and the triple bar an F. Okay, if a ampersand is T, then we know that both of the conjuncts are true. So, true and true. Okay, over here, if a triple bar is false, that means that P and Q do not have the same truth value. So, what we can do is we can pretty much just go ahead and assign that P is T and Q is F, just for current things. However, we have Q being F, P being T, T, F. Then we have issues here. So let's do it the other way around. Let's try Q being T and P being F, which doesn't change anything for the triple bar. And if we know that this is wrong, then we know that this is not truth functionally equivalent. And okay. Alright, now Q is T, P is F. Again, we run into issues. Okay, T then F and horseshoe does not make T. F then T and horseshoe does make T, but we run into issues here. So, therefore, this sentence, or these two sentences, are not equivalent. That's pretty much just how you do it. You assign the F to one and T to the other, and if over here everything works out, then it's actually, I got that wrong. Because this worked out, then it's not. Wow, I'm stupid. Because this whole thing worked out, then it's not functionally equivalent. However, since this whole thing worked out, since this didn't work out, then we know that this one is. Gosh, I apologize about that. That's stupid of me. What we're doing is we assign T to one, F to the other, and if it works out, then we know that it is not truth functionally equivalent, because they can be different truth values. However, if nothing works out here because this one didn't work out, then we know that they both are truth functionally equivalent. Okay, now on to consistency. Consistency, again, we have, let's say we have a set of sentences of these two and another set of sentences of these two. So we want to basically assign T's to both of them. And if everything works out, then we know that they are both, that the set of sentences between these two is consistent, because it's possible, given a truth value, that they both come out as true. However, if it doesn't work out, then we know that they are not consistent. So Um, what do we know here? A ampersand being true, that both of the conjuncts have to be true. And given that, we know that Q is true. And given that Q is true here, P must also be true. Okay, T then T is T, checks out. T and T makes T in triple arc, T and T in a ampersand, checks out. So this is true functionally consistent set of sentences. Okay, over here we again assign the same thing. We got to figure out what our dominant connective is, our dominant operator. We assign T to them, and again we will have ampersands. We know that it's both T. Q is T, and that would make P also T. And again, it checks out because Q and P makes, or T and T makes T, T and T makes T, so that checks out. Let's see. T and T in a triple bar makes T, T and T in an ampersand makes T. So again, that's also true functionally consistent. So I'd like to do one more problem of consistency, where we know that they are not consistent. So we have P and we have Q. We know this is our ledger. So we'll do this first. P horseshoe Q. Then we'll do tilde P horseshoe Q. And we know that that those are not consistent. We can't have those both in a set and have the whole thing work out. So we'll do T, T, and this T makes the dominant operator inside this become an F. And we know that for an F, a horseshoe means T and F. So we know that P is T and Q is F. T and F. But we have an issue here because T and F makes an F in a horseshoe, but we have T. So we know for a fact that this is not, we know this is for a fact not consistent. I mean, that's obviously, these two are obviously not consistent because this is P horseshoe Q and this is not P horseshoe Q. So those in a sentence would not work out because they are contradictory. So that would totally just fail. But I wanted to do that just to show how that when we run into issues, we know that we have a set of sentences which are not consistent with one another. So I kind of did mess up at the beginning there. I kind of I pretty much got my stuff switched around, so I apologize about that. But hopefully I got it straight, and hopefully that was okay. But if I messed something up, other than the one time that I know I did, comment below. And if you have a question, also please do comment below, because whenever you comment, I get an email. If your comment is constructive, then I will always respond. Thank you.